Hello everyone and welcome to another video. Today I'd like to continue our discussion on partial differential equations focused on the heat equation. So you might remember that in our previous video we discussed how to derive the general heat equation, and we saw that this actually involved a function of four independent variables. There were three spatial variables, x, y, and z, as well as a temporal variable time t. Now, finding a function of four independent variables is actually going to be a little bit difficult to talk about at first. So in this video, I'd like to look at some simplifications to reduce the dimensionality of the problem so we can solve an easier problem and gain some insight into how the problem behaves. Once we simplify the PDE, we'll apply the separation of variables technique to break this PDE down into a pair of ODEs. You might recall that this is actually the same method we applied when solving the 1D wave equation, which is over there. As such, I would encourage you to view the video entitled Solving the 1D Wave Equation before watching this particular video. Most of the insight and discussion into the details of the separation of variables technique is contained in that video over there. So to avoid duplicating content, I'm going to go fairly quickly over it when we apply it to the simplified heat equation in this video. So if all of that sounds like a good plan of attack, why don't we jump over to the whiteboard and get started. Alright, so like we said, what I'd like to consider right now is simplifying the problem a bit. So I'd like to talk a little bit about the 1D heat equation. So what I mean by that is, let's remember or recall what was the overall heat equation. Let me just switch pens here. That pen's a little bit odd here. So if you remember here, last lecture, what we derived here was the governing equation for the heat equation, right? So this was partial u with respect to t, right, minus c squared Laplacian of u has got to equal 0 here. In this case, right, if you remember, the function we're looking for here is the temperature distribution as a function of x, y, z, as well as time here, right? That's what we're looking for. This is our temperature distribution. And here we said c here was this concept of the thermal diffusivity. I guess technically c squared is the thermal diffusivity here. And this was given by the thermal conductivity divided by the specific heat times the density here, right? So this was here our thermal diffusivity. And again, you could just think about this as just a constant number. It's the one constant parameter here in this problem here. And like we said earlier, del squared u here is the Laplacian of u, right? Which we said the Laplacian, if you remember our discussion on vector differential calculus, this was just the sum of all the second order partials of the spatial terms, right? So it's du dx squared plus du dy squared plus du dz squared, all right? Okay, so you see here, this situation has four independent variables. Let's see if we can knock this down to just two independent variables. So what I'd like to consider here is, let's look at an example of a long, thin bar. So in other words, let's say I've got some bar here that is long and thin here, and it only runs in the x direction. So I'm just going to draw the x-axis like such here. So here's the x-axis. So it starts here at x equals 0. And ends here at x is equal to L. And it really has no dimension or depth in the y or in the z here. So it's this concept here of a one spatial dimension system here with one temporal dimension t. So that's just maybe a quick note here. This is sometimes referred to as the 1D heat problem or equation. Let's write that down here. So in this case here, where there's no x or y here, you can see that these terms don't contribute, right? The du dy and du dz are 0 here. So really what the overall heat equation reduces down to is something a little bit simpler here. So we could rewrite this thing as partial u dt, right, minus c squared partial u dx squared here is equal to 0 here. So this is sometimes referred to as the 1D heat equation. And just a quick note here, you might say, okay, why are you calling this one-dimensional? Because there's clearly a spatial dimension and a temporal dimension. So there's two independent variables, but the 1D refers to the one spatial variable. So we're only considering the space in x here, even though it's two independent variables. It's referred to as a 1D problem here, okay? All right, so with this as now our simplified governing PDE, let's go ahead and apply some boundary conditions to this here. So let's say, how about boundary condition of, let's say that this bar is perfectly insulated. So, you know, maybe we wrap this thing in, I don't know, some towels or some perfect insulator. So heat doesn't go in any direction other than the X direction here. So this is an insulator on both sides here. And what we would like to do is we'd like to fix the temperature at either end of the bar. So maybe we stack this up against a block of ice or something like that. So maybe I'll draw this in another color. Maybe I'll draw a big cube of ice here and a big cube of ice on the other end. Or maybe you stick an oven on one end and a cube of ice on the other end. But long story short, we'd like to fix the conditions at the two endpoints. So in this case, let's go ahead and use this ice example here. So we'll use a boundary condition of fixed temperature at endpoints. So if that's the case, what we're looking for here is the function u that we're looking for as a function of x and t here. What we would like to say here is x at the temperature at x equals 0, and at any given time, let's say that's equal to 0. So this is basically, again, the left side condition. And then let's also say that the temperature at x equals L, the far side, is also equal to 0. So this is the right side. So again, both of this is basically the situation of saying that both ends stay at 0 degrees Celsius or whatever we have this thing set at, okay? All right. Here's our boundary conditions. How about let's specify an initial temperature distribution as well here. So how about an initial condition of, okay, the temperature here at any given x location and at time 0 here is going to be some function f of x here. So maybe it's really hot in the middle here, or maybe it's this sinusoidal temperature distribution, or who knows what it's going to be, but it's going to be some function of x. We should maybe just here note that, you know, in order to make this problem consistent here, this functional distribution, it can be anything it wants as long as it satisfies the left and right conditions as well. Because otherwise you have this kind of conflicting situation. So what we should mention here is that we should say that, all right, f of 0 and f of L, that also better equals 0 in order to be consistent with above, right? To be consistent with the boundary conditions. Okay, so if we have this set up, we've got our simplified 1D heat equation here. We've got our boundary conditions. We've got our initial condition. I think this is a fairly well-posed problem. We can go ahead and apply our separation of variables technique to this. And if you remember, again, we talked about this at the intro of the video here, but we've discussed the separation of variables technique when we solve the 1D wave equation. It's going to be very similar here, so I'm going to go over this fairly quick here. So let's just jump through our three steps, right? So step 1 here was we are going to apply the separation of variables. All right, the whole goal of this thing here is to get 2 ODEs out of this single PDE. Step 2 here was we're going to go ahead and determine solutions that satisfy boundary conditions. Again, let's abbreviate those as BCs. And finally, step 3 here was we are going to now use Fourier analysis / techniques here to get a solution that satisfies the initial conditions, right? To obtain solution that satisfies ICs, right? So that's our game plan. So let's go through this quickly here. Again, this should be Very familiar from our discussion of the wave equations, so we'll gloss over a lot of the details. If you would like the details of any of these steps, please see the 1D wave equation video that we referred to, and it's in the description of this video here. So step 1, this is our separation of variables, okay? So what we said here is we're going to assume that the solution that we're looking for here is going to be able to be written as the product of a spatial function with a temporal function, right? Okay, and now if we go ahead and do the same thing we did earlier and sub this into the original PDE here, right? If you remember, what was our PDE? I think it was partial u with respect to t is equal to c squared partial u with respect to x squared, right? So just jam this into here, and I'll just say dot, dot, dot to basically say, you know, I'll let you work this out on your own here, or watch how we did this in the wave equation expression. We can basically manipulate this thing to look like g dot over c squared g is equal to f prime prime over f here. Right? So we see, again, we isolate, we get all the temporal stuff on one side, the spatial stuff on the other side. The only way the two things are going to be equal here is if they have to equal some constant, or our separation constant. Let's call this thing k. And then, just like we talked about earlier with the wave equation, you can show that this k value has to be negative, right? So in order to denote that, let's just say I'm going to call this thing a negative p squared, right? And this is less than 0 here. So again, what I'd like to do now is just denote here that our separation constant has to be negative. So I'm going to use this notation to demonstrate that here, okay? So in this case, what we do is we obtain two PDEs here, two ODEs. So the first ODE is f prime prime of x, right, plus p squared f of x is got to equal 0. And the second ODE is g dot of t plus c squared p squared g of t has got to equal 0 here. So here's ODE 1 and here's ODE 2. Great. Okay, so let's box these two guys up. That's the end of step 1 here. We got ourselves our two ODEs. So let's go ahead and move on to step 2 here. So we would need to satisfy our boundary conditions, right? Okay, so in order to do that, remember our boundary conditions, we said that, all right, the temperature on the left side of this thing had better equal 0, right? So if this is the condition we need to hold, what does that mean f and g have to look like, right? So if you plug this in, we see that, all right, that means f of 0 times g of t had better equal 0 for all t here, right? And similarly, on the right-hand side, u of lt is going to see f of l g of t has got to equal 0 for all t here, right? Okay, so let's go ahead and use these conditions here and try to solve. How about let's start with ODE 1 here. So let's go ahead and say solve ODE 1, right? So we can first go ahead and use our first boundary condition here. So what we should do here is, let's say, apply BC1. Maybe we should have labeled this here. So this first one, this is boundary condition 1, and this is boundary condition 2 here, okay? So let's apply the boundary condition 1. Basically, what does the left side of the bar have to look like, right? So in this case, we see that boundary condition 1 is basically saying that f of 0 has to equal 0, right? You get that here, right? Since g can be anything, the only way this is going to be true for all t here is if f of 0 is 0, okay? So here's the initial condition to this ODE, and if you look at this ODE long enough, you see same thing like we did earlier. We realize this is a second order undamped homogeneous linear ordinary differential equation. So its solution here is a bunch of sines and cosines, right? So its f of x is going to be basically, let's call it a cosine px plus b sine of px here, right? And now we can go ahead and let's apply this initial condition to this solution here. So what we see here is that when I plug in f of 0, when I plug in 0 for x, right, I get a cosine of, so that times 1 plus b times 0 has got to equal 0 here. So if you look at this thing long enough, this is basically saying that a has to equal 0, right? Okay, so that's one thing we've got. Let's go ahead and now apply the second boundary condition. Okay, so now let's go ahead and apply BC2, right? Which said that f of L has got to equal 0 here, right? So f of L is going to be a times cosine of PL, right, plus b times sine of PL, right? And this had better equal 0 at the end of the day. We just saw that a's got to be 0. So again, this term is gone here. So we end up with a relationship here that b sine of PL has got to equal 0. We're going to make the same argument we did when we were doing the wave equation here, and we see that, all right, in order to obtain a non-trivial solution, P has to take on very specific values. In other words, if you look at this long enough, P has to be, the combination here of, PL has got to equal some multiple of pi here, right? So that the argument to sine is some multiple of pi, so it always equals 0. So in other words, P has to be very specific values. It has to be n pi over L for n in the integers, right? Great. So combining this here, I think we have a reasonable solution for the spatial function f here. So let's write this down here. So combining, we obtain that, all right, the spatial function has got to be something on the order of b sine of n pi over L x, right, for n in the integers. And again, let's adopt this notation that we see that since n can be integer values, let's call this thing fn here, okay? Great. Box this guy up. We've gone ahead and solved the spatial ODE. Let's go ahead and now try to solve the temporal ODE. Okay, maybe I'll leave some of this up because we might use this here in a second. Okay, so let's go ahead and say we now would like to solve ODE2. All right, so this ODE, which again, you stare at this thing long enough and you see it. Hey, that's actually what? That's actually a first order linear homogeneous ordinary differential equation, right? It's first order because I only see a single dot. It's g dot, right? So its solution here, well, maybe we should write that down. So let's just say we recognize ODE1 as a first order linear homogeneous ODE. So its solution is like, it's like e to the lambda t or e to something t. So solution, and the lambda in this case, you can kind of see it right here, right? Here's the time constant of this thing. So the solution right off the bat here of this thingy is it's g of t, right, is going to be equal to, where did I put this here? Oh, sorry. You know what? I skipped a step to make ourselves, sorry. Let me back up a step here. This is gonna make our life a little easier here to see this. Let's rewrite our ODE here. So again, our ODE here is g dot of t plus c squared p squared g of t is equal to 0 here. Okay, so let's rewrite this sucker here. So this is now g dot of t plus wait a second, what did I do here? Okay, sorry. Yeah, I got way too excited and jumped 2 lines here. What I want to do here is let's take a look at this separation constant p here. So if you recall, right, earlier I think we said that this value p here, that was part of our separation constant, and we said that it had to be negative. So in other words, we had the separation constant k was equal to minus p squared, right? And what we also just saw earlier here when we were solving ODE1 here, I'm trying to see if I also kind of glossed over that fact here. No, we did it right here, right? We saw that P can't be anything you want, right? P has to be very specific values here, right? So P is not completely free. It has to follow this equation in order to be reasonable here. So a couple things we got to note here. So we're going to note that the separation constant was minus p squared, and also we said that P has to be n pi over L. right? Okay, let's substitute all of this in for p here to make this a little bit easier. So what we can do is we can rewrite this differential equation here as g dot of t plus, if you do all the algebra, you can get it to, and massage it to look like cn pi over L squared g of t is equal to 0. There we go. This is a little bit better here. Okay, and now why don't I call this thing in parentheses, let's just call this thing lambda, and maybe lambda sub n, right? Because we see that n is an integer value. So there's going to be a value for n equals 1, 2, 3, 4, 5, etc., right? So let's call this thing lambda here. So finally, we see that, all right, this ODE number 2 here, all we're doing is rewriting this thing to look like g dot of t plus lambda n squared g of t is equal to 0 here. And our lambda n is where it's cn pi over L here, right? Okay, so maybe we should box this up here, because all we're doing here is I'm rewriting ODE2 into a little bit more recognizable, easier to work with form here, because again, yeah, you can see here's the time constant if you want to think about it that way here, and here's what that time constant is related to the physical parameters of the problem, namely the thermal diffusivity here and the length of the bar here, right? Okay, so now, yeah, again, like I said, I apologize. I got way too excited about this statement here, which still holds true, right? We still recognize this ODE here as a linear first-order homogeneous ODE. So its solution here is readily admitted here to be something like what? It's g of t is equal to some constant, let's call this constant, how about bn, right, times e to the minus lambda n squared t here. And again, since the solution here is good for n in the integer values, maybe let's adopt the notation gn here, right? So each one of these admits a family of solutions, right? Okay. So great. So now let's box this up, because now what we've got here is we've solved the temporal portion of the separation of variables. We've solved the spatial portion of the separation of variables. So let's jam those two things together to get eigenfunctions of the problem. So our eigenfunctions, right, were basically u of xt is equal to the spatial one times the temporal one, right? And we adopted this notation of sub n, right? Because each one of these had a different solution depending on n equals 1, 2, 3. So again, our eigenfunctions we have n eigenfunctions. So again, let's adopt that notation here. So let's just plug in our expressions here. So we end up with this thing looking like, where did I have this thing? Right, okay, so this is b sine of n pi over Lx times bn e to the minus lambda n squared t, right? Great, and then now if you notice here, this b and this bn, they're just arbitrary constants, right? So there's no need to carry around two arbitrary constants when I can just jam the two of them together. Heck, it's a product of two constants. That just gives you another constant. Again, let's just call it bn, how about? So what we end up here with is bn times sine of n pi over Lx times e to the minus lambda n squared t here with n in the integer values here, right? Okay, here we are. So here's our eigenfunction here, right? So here's our eigenfunction here with an eigenvalue here of lambda n here, which we said earlier down there was cn pi over L here, right? So great. We've got our eigenfunctions, we've got our eigenvalues here, so I think we're pretty much ready to go. So you could run over to Mathematica here and verify that this solves all the boundary conditions of the left side is equal to 0 and the right side is equal to 0. And you know, if you plug in x equals 0, yeah, this all should work out here, right? So we saw that in the 1D wave equation. I don't think we need to go run over to Mathematica and do it here. So I'll just leave this as an exercise to the viewer here to show that this function solves the boundary conditions that we've set up here, right? Okay, so great. Let's go ahead and do now step 3. So step 3 here is we want, all right, I don't want to just satisfy the boundary conditions, I want to satisfy the initial condition as well, all right? So we're going to go ahead and do step 3, which is our use Fourier analysis to compose a solution out of all of these eigenfunctions here, right? So step 3, right, was satisfy our initial conditions here, right, via Fourier. Right, that's what we're going to do. All right, so what I'd like to do now is I want to come up with a total solution here which satisfies both the boundary conditions and the initial conditions. And the way I'm going to do that here is I'm just going to go ahead and let's jam together or sum from n equals 1 to infinity all of these eigenfunctions that we've cooked up here, right? So we are going to sum from 1 to infinity all of the eigenfunctions. Right? And I guess if you want to write this out one more term here, right, this is sum from n equals 1 to infinity here of bn e to the minus lambda n squared t times sine of n pi over lx here, right? So I've just flipped the order here of the exponent and the signs here. Again, since they're multiplied together, it doesn't really matter, but it's going to make the comparison a little bit easier here in a second, okay? Okay, so now let's go ahead and say I need to satisfy the initial condition, right? In other words, I want to look at this thing when time equals 0, right? So I need u of any x at time 0, which is going to basically be my candidate solution here. As we said, it's going to be this thing with time equals 0. So luckily for us, if you do that, you see time equals 0, this whole term, the exponent goes away here. So we end up with this thing just looks like bn sine of n pi over lx, right? And what we said here is I want this candidate solution to equal the specified distribution f of x here, right? So this here was given initial condition or temperature distribution. Okay? So the game plan at this point is I just need to find all of these b coefficients that are going to make the left-hand side of this infinite sum equal this arbitrary function here of x. That should be ringing bells in your head of basically saying this is what Fourier analysis did. Right? Fourier analysis says take a bunch of sine waves or cosine waves or combination of sine and cosine waves and add varying amplitudes of these functions to each other here to make yourself equal to some arbitrary function. So again, check out the wave equation discussion or solution video if you want to see the gritty details of this here. But what we saw here is that just by applying Fourier analysis and expanding our initial condition f of x as a I think we do a odd function and expanded, yeah, I think we extended it as an odd function, and its half range expression was basically exactly that format here. So maybe let's just say from from odd expansion of f of x, we basically get here that these bn coefficients here are directly given by the Fourier formula here, right? So it's 2 over L integral from 0 to L f of x sine of n pi over L x dx here, right? For n equals 1 to yada, 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 right? And in the integers, I guess is maybe how we should have just said that, right? Okay. So great. So I think boxed this up because this is what we are looking for here, right? This tells us how to calculate the coefficients here of the Fourier series here. Then we basically just need to well, I guess calculate an infinite number of these things here to get our actual initial temperature distribution. But I don't think I want to go to infinity. So let's maybe think about some partial sums and just take up, I don't know, 10, 20 terms or something like that. Okay, so now that we've got all this, let's go ahead and look at an example here of this thin bar here. So let's think about this thin bar with a, how about a sinusoidal initial condition here, okay? So what I mean by that here is, let's just choose some constants for this problem here. So what we're looking at here is, let's choose a copper bar. And Again, we'll use the same boundary conditions that we've set up. And actually, we should mention here, I guess the whole derivation here was set up for boundary conditions of 0 degrees on both sides. So we really can't screw with this here. Otherwise, we're going to have to rederive things here. So let's just use the same boundary conditions here. So 0 at both ends. Okay. I think that seems pretty reasonable here. Okay. All right, so the reason we wanted to look at copper here is copper here, you can go ahead and look up things like its density here. So the density here is, I think, 8.92 grams per centimeter cubed. I'll let you convert that to kilograms meter cubed if you want to work in SI. Copper, you could also go ahead and find things like its specific heat. So sigma here, the specific heat of this thing was, I think, 0.092 calories per gram degree Celsius here. Again, feel free to convert if you like here. And then its thermal conductivity K here is something like 0.95 calories per centimeter second degree Celsius. All right. I guess these should probably be in parentheses for the units. But anyway, who cares? Mishmash of numbers here that are going to be able to smash this thing down to our constant of the PDE. So that's all we wanted to do here. And now let's go ahead and look at an initial condition here of f of x is something like 100 sine of pi x over 80. Okay. So, all right. And let's go ahead and say that the length of this thing here is 80 centimeters. Okay. So tell you what, let's work with x in centimeters here, and the reason why is you can kind of see here that when x is equal to 80 centimeters here, we get this to be 0 here, right? So in other words, if you plot out f of x here, let's plot our initial distribution here of temperature, f of x versus x here, right? So here's x equals L at 80 centimeters here, and all this thing looks like is a sine wave, exactly like this, with, I think, magnitude here of 100 degrees here. So it's hottest in the middle of the bar here. So this bar starts off here with this distribution. So it's like we had the blowtorch that we were showing earlier, but I just cooked the middle of the bar here and the heat has kind of diffused. And as soon as it's diffused to this sort of sinusoidal pattern, I want to start the experiment and see how does the heat diffuse here. Keep in mind here that what we've said is the ends of this thing are always 0 degrees here, right? So I'd like to see the heat flowing from the middle, hopefully moving out to the edges, and eventually this whole bar should probably come down to 0 here is the scheme. Okay? All right. So if we have all of this, I think what we can do here is start applying our solution that we just got. So first thing we can do here is we can probably go ahead and get these coefficients Bn, right? So all I got to do is take this f of x, jam it into here, and start cranking away at this integral here. So again, that's kind of boring, busy work here. Feel free to do this in Mathematica or some other tool if you'd like. Let's go ahead and take a gander at that here. So if you do that long enough here, if you basically go ahead and try to calculate Bn, right, and you plug in 2 over 80 times integral 0 to 80, right, of what's our f of x, times 100 sine of pi x over 80 times sine of n pi over 80x dx, right? This is just, you can see here, this is just this one silly integral with respect to x. Go ahead and do this in Mathematica or do it by hand. I don't think it would help to just to have me do this out here on the board here. What you're going to end up with here at the end of the day here is you'll get something as a function of n here, right? N is the only thing that's going to survive out of this thing. And what you end up here with is actually 200 times sine of n pi all over pi minus n squared pi. Okay, so here we go. Here's our Bn coefficients here, right? Okay, now what you might be tempted to do here is say, all right, you know what? Since I now know these Bn's, I can get my total solution here, right, as just summing up n equals 1 to, I don't know, maybe let's call it p, right, terms, and maybe we should call this UP here, right? So this is a partial sum here. So this is what we did with the 1D wave equation, right? We said I don't want to sum to infinity. I'm just going to go ahead and do a few of these terms here, right? So this would be you know, a bn e to the minus lambda n squared t times sine of n pi over lx, right? Okay. Right, this was my eigenfunction. I now know how to calculate the Fourier coefficients for this eigenfunction. So you might just say, all right, let's go ahead and do this. Now, what's kind of interesting is what happens when the very first time you do this for n equals 1. Look at this expression over here. What do we end up with for, let's try to compute b1, right? What is b1? This is 200 times sine of 1 pi all over pi minus 1 squared minus pi here, right? What's the numerator come out to be? That's the big fat 0 over crud. The bottom is 0 also, right? So this is, we're a little bit screwed here, right? This is indeterminate here. So, you might be scratching your head here. So to get around this, you know what we should do is let's write out the entire partial sum, maybe a couple of terms, and I think we'll get the pattern here, right? So what I'm going to do here is let's go ahead and write out the you know, actually it doesn't have to be the partial sum. Let's just write out the total solution. Right, so what we said here is, all right, you know what? Let's do, and actually maybe more importantly, we should write out the total solution at time t equals 0 here, right? So the total solution, u of x at time equals 0 here, right? It's going to be summation from n equals 1 to infinity here of bn e to the minus lambda n squared 0 here, right? Times sine of n pi over lx. Right? Okay, so again, this term, oh, sorry, whoops, I didn't try to calculate, I try to get the b, right? I'm trying to just get the exponent. The exponent just goes to 1 here, right? So this thing becomes summation from n equals 1 to infinity of bn sine of n pi over, I guess what was L in this case? I think it was 80, right? 80 centimeters, right? Okay. And what this is trying to do here is we're saying, all right, the initial temperature distribution, this better equal my specified initial condition here, right? So what I'm trying to do is I'm trying to find the Bn coefficients and make the left-hand side equal to the right-hand side. We had that expression for it over there, but we saw that something happened here at n equals 1 that kind of choked up our problem. So you know what? Let's write this out a little bit here, right? So this is B1 times sine of 1 pi over 80x here, right? So that's the n equals 1 term, right? Plus B2, right? Sine of 2 pi over 80x, right? Plus B3, right, times sine of 3 pi over 80x, plus et cetera, plus to infinity here, right? Now, let's write out the left-hand side. The initial temperature distribution, what was that? I think we said it was 100 sine of pi over 80x. I think, let me just double check. I don't want to misquote this. Yeah, right? Okay. So now, if you look at this thing, right, just check this out. Here's sine of pi over 80x, sine of pi 80 over 80x. So actually, if you compare the left-hand side to the right-hand side, you see here that the way to make the left-hand side equal to the right-hand side is what? B1 had better equal 100 here, right? So we see B1 has to equal 100, and then B2 had better be the same as B3, had better be the same as B infinity here, right? Those all have to be 0, right? All these terms don't contribute to this problem here, right? So gone. So here we are. So here's another way to kind of ride this donkey here is instead of trying to analytically compute the coefficients here, we could do this sort of by comparison. And we see directly here that B1 is equal to 100, right? Okay, so you know what might be kind of interesting? At this point, I think we've got this problem licked here because now we have the coefficients here, therefore we have the total solution. Yeah, I think we're good to go. Let's run over to Mathematica here and maybe animate or simulate and see how does the temperature actually dissipate through this thin one-dimensional bar. All right, so here we are in Mathematica. So let's go ahead and maybe first let's go input the initial condition. And maybe we can try to visualize this as well here. So I think we said, all right, f of x was 100 sine of pi x over 80, right? That was our initial condition. And let's just go ahead and plot that as well from the range of x going from 0 to 80 centimeters here, right? So we can get an idea of what this thing looks like. And here we go. Here's our initial temperature distribution. So now let's go ahead and input our problem constants, namely things like the density here of copper. I think we said was we're just using a number of, what was it, 8.92 here. Sigma was 0.092. Again, I'm not being too careful about this being an SI or anything because, as we saw, all this is going to do is just change the constant of the problem here. All right, and the length of this thing was 80 centimeters here. Okay, so maybe let's based on this compute that intermediate variable, right? We saw that the one parameter of the 1D heat equation was this parameter C here. Right, and I think we said C was given by K over sigma rho, and then we had to square root that thing, right? Okay, so in this case, the C parameter is some machine number, 1.07. Okay. All right, so now that we've got this C number down, I think what we can go ahead and do is get ourselves our eigenvalues here, right? So let's define lambda n, right? So I think we said our lambda n as a function of n here was Cn pi over L, right? Great. And you know what? Now that we've got our eigenvalue, we can go ahead and define our total solution, right? So on the board, we said that the total solution was denoted as u of xt here, right? So I think in this case, we said u of xt is just going to be 100 times e to the minus lambda 1, right, squared t times sine of pi over Lx, right? That was our total solution. So shift enter that. And again, we see it's just a function of f. Or sorry, a function of x here. So now let's go ahead and verify that this satisfies the original PDE, right? So we want to make sure that, tell you what, instead of calling it that, let's just verify that u of xt, right? Verify that our total solution satisfies the original PDE. So if you remember, our PDE for the 1D heat equation was we had to take u of xt and take its derivative, with respect to t, right? So here's partial u with respect to t minus c squared, and then I needed partial u with respect to x twice, right? So that should equal 0 here, right? And let's shift enter that, and that seems like it is not quite 0. But if you look at this thing long enough here, right, you see what's going on here is we're dealing with imprecise or imperfect inputs, right? Because I use a lot of these decimal point inputs way up here in the problem constants, we see that, here, 10 to the minus 17th, that sure looks like numerical round-off error. So in order to get Mathematica to kind of ignore that round-off error, I'm just going to say / chop. Okay? Or I guess, you could wrap the chop over here, and I could just say, take whatever you get over here on the left-hand side, chop off any I need to click over here. There we go. Chop off any numerical error and make that equal to 0. There we go. So that's true. So we see, yep, this satisfies the initial PDE. So let's go ahead and check now. Does this satisfy or verify u of xt satisfies the boundary conditions here, right? So in order to do that, we said, all right, u of 0t, right? This better equal 0. So this here was our left side is constant at 0, right? And then we also had to check that the right side, or when this thing was equal to L, that was constant. And there we are, true, true. It's both true. Great. So the last thing we want to do here is let's go ahead and verify that u of xt satisfies the initial conditions. Right? So what I'm looking for here is the function, our total solution at time 0, better equal my distribution f of x. And yay, look at that. It all worked out. So I think we're great. This thing totally works here, at least from a mathematical perspective. What we might want to do here is now let's just go ahead and animate the scenario so we can see what this looks like. So what I'm going to do here is let's just generate our plot here. Plot of u of xt running from x going from 0 to L here. That's like our inner plot here. And maybe we should let's just do this at time equals 0. Right? Okay, good. This is looking pretty reasonable. Maybe what we should do here is let's add some plot labels here so we can see what's going on here. So plot labels, we said that the title of this plot is something like maybe u of xt here. And let's go ahead and add some axes labels. And we'll go from the x value should be labeled as x. The y value should be labeled as the temperature distribution. And the last thing that we may want to do here is let's make some, let's specify the plot range here. So we're going to make this go and plot over a very specific range of values here. So let's make the x values go from 0 to L. And we'll make the y values go from, I don't know, maybe 0 to 100. Okay, and then we're going to do this right now because it's going to make our life a little easier when we try to manipulate this thing. Okay, so great. All right, so this looks all great right now, but again, I want to see how this changes with the function of time here. So let's wrap this whole thing in a manipulate here, and we're going to manipulate time here in our function u of xt here. And coming outside, let's go make t go from 0 to, I don't know, 1500 seconds or something like that. Okay, so if we enter that, here we are. Here's our new plot, and what we can do now is we can see here's the initial temperature, right? It's really hot in the middle of the bar, but if I go ahead and hit play, here we go. So heat is flowing out the ends here, and they're staying at 0, and we see that the temperature eventually is going to come down to actually equilibrium, which is equal to what the bar ends look like. So here we are. I think this is a pretty good solution here to our 1D heat equation here. So if you enjoyed this video here, please subscribe to the channel. It really helps me continue making these videos here. And we are going to have a couple of other videos coming up. In fact, the next video I like to do here is looking at the heat equation. And instead of looking at how it's going to vary in time, let's think about how it might vary in space, maybe in x and y here. And we're going to see that actually results in what's referred to as Laplace's partial differential equation. So, with that being said, I hope to catch you at that future video. Bye!